In the previous video, we saw how one thread can disrupt the predictability of our code by updating another thread's values. In this video, we're going to see how locks can fix this issue by disallowing concurrent multi-threaded access to small bits of code. We'll start by opening our previous project and build and run right away to see the issue at hand. So, the problem we're facing is that we're running two threads concurrently and we don't have any isolation between them, so their operations are updating our value out of sync. We're going to address this by introducing NSLock. An NSLock object is used to coordinate the operation of multiple threads of execution in an application. We can use NSLock, which utilizes standardized POSIX threads, to mediate access to an application's global data, or to protect pieces of our code from being accessed by multiple threads at once, allowing it to run atomically. I'll add a link to more resources regarding POSIX threads on this video's resource page. We'll add a class property and give it an initialized value of NSLock. Then, inside of our first loop, we'll call our method on our NSLock object that tells our application to effectively lock access to one thread at a time. Now, if we run this code right away, we'll find that our application gets deadlocked, as we'd be running our lock method without ever unlocking it. When we lock our thread, we are effectively telling our program that no other thread is allowed to access this code until our current thread finishes execution of our code and hits the call to unlock. Since we never unlock, we never grant access to the next thread to run, and this is what's described as a deadlock. So we need to add an unlock function after the code we're trying to isolate, which, in this case, is just before the end of the loop. I should add that it's important to call unlock on the same thread in which we called lock in order for this to work. When using locks, we're actually forcing threads to wait in line to run, which can ultimately result in longer execution times. So, we want to lock only the crucial points of our data. Now, what we've locked here are the points where our value gets incremented. Of course, we should also lock and unlock the points where our value gets decremented as well. Now that we have our locks in place, we can build and run our application. This time, our program runs as expected, incrementing to 5,000 and decrementing back to 0. To visualize how this works, let's compare the clip we saw in the last video to how our code is working here. Previously, as our threads ran concurrently, they would fight for their turn to access our value. With locking in place, we now force the other threads to wait their turn before entering our for loops, which stops them from disrupting our sequence of operation. Of course, this has been a very simple example designed to illustrate how threads can disrupt one another if used improperly. In this video, we have seen how introducing locks can protect our global data from being mutated from other threads. In the next video, we'll look at asynchronous methods and how we can use completion handlers to force our code to wait to execute.